The topic of chapter 14 is cardiac output, blood flow, and blood pressure. Cardiac output is the volume of blood pumped each minute by each ventricle. So it's a volume per unit time. So for example, it's often expressed as milliliters per minute, or it could be expressed as liters per minute. The average cardiac output for an adult is about roughly 5,000 to 5,500 milliliters per minute. So the cardiac output is simply the product of the stroke volume, which is the amount of blood ejected by the heart with each heartbeat, multiplied by the heart rate. And again, the typical units would be milliliters per beat and beats per minute. The average heart rate of an adult is 70 beats per minute, and the average stroke volume is 70 to 80 milliliters per minute per beat. So if you think about it with this cardiac output of 5,500 milliliters per minute, that's actually quite close to the average blood volume of an adult, which is around 5 to 5.5 liters. So this means a drop of blood will essentially make a round trip through the cardiovascular system each minute. I've mentioned this before, but it's worth repeating, which is that you essentially have two pumps in your cardiovascular system. You have a right pump and a left pump. The right pump creates the pressure that's needed to move blood through the pulmonary circuit or pulmonary circulation, and the left pump creates the pressure that's necessary to move blood through the systemic circulation or systemic circuit. Now, these two pumps are quite different. The left pump creates a higher pressure, and we can express that as a mean arterial pressure, or MAP. And that's going to be about 70 to 105 millimeters of mercury, okay? So that's the pressure you'd find in the aorta. It's the pressure you measure from the brachial artery in the arm. The pulmonary circuit doesn't require quite as high a pressure. So the mean arterial pressure of the pulmonary circuit is only 10 to 20 millimeters of mercury. So it's much lower by roughly about a factor of 5 compared to the systemic circulation. So given that the fact that these two pumps are a little bit different in terms of pressure, students often think, well, maybe the output of the two pumps is different. Well, it turns out the cardiac output is exactly the same. And it makes sense, right? It's all one big circuit. So the blood has to make its way around the entire body, including both circuits. And so the cardiac output of the right ventricle is exactly the same as the cardiac output of the left ventricle. So you might be thinking, well, how is that possible, given that the pressures are so different? Well, it turns out the resistances of the two circuits are quite different. So the resistance of the systemic circuit is much higher compared to the resistance of the pulmonary circuit. And so the pulmonary circuit can have the same amount of blood flow, in other words, the same volume per unit time as the systemic circuit, with a lower pressure gradient. And the reason is because the resistance, the vascular resistance to blood flow is much lower. From one moment to the next, the cardiac output has to change. A good example of this would be going from, say, resting to suddenly exercising. Your cardiac output will have to increase to supply oxygen and nutrients to the working skeletal muscles in the arms and legs. So just as a reminder, cardiac output is simply equal to the product of stroke volume and heart rate. So in order for cardiac output to increase, we would expect stroke volume to increase, perhaps when we're exercising, and we might also increase heart rate. So the question then is, how are stroke volume and heart rate regulated? Recall that your heart is myogenic. It generates its own rhythm. So even if you were to remove all the nerves going to your heart, it would still generate a rhythm of roughly about 90 to 100 beats per minute. So, and the reason that you have this myogenic rhythm is that there are modified cardiomyocytes in the right atrium in what's called the SA node or sinoatrial node. These cardiomyocytes have special channels in them, and they generate action potential spontaneously over and over again at a certain rate. They have some special channels that allow them to do this. One is the HCN channel. This channel is a little bit unusual because it opens in response to hyperpolarization of the membrane potential. So, for example, if we see at the end of an action potential, as the membrane repolarizes, you now have a hyperpolarization. Well, that leads to the opening of these channels, and through these channels, you'll have influx of sodium. So this is a positive ion moving into the cell, so this will then depolarize the membrane. Now, it turns out that these channels are also equally selective to potassium, and so you'll have an efflux of potassium through the same channels. But as we talked about before, the driving force on sodium is greater than the driving force on potassium because the sodium equilibrium potential is up at plus 60 millivolts, so it's way up here, whereas the potassium equilibrium potential is about negative 90 millivolts. So because of this difference, there's more sodium influx than there is potassium efflux, and therefore you get this depolarizing effect. And so you then get what's called a pacemaker potential. This potential gradually rises up. It will eventually get to a point where you reach spike threshold. And normally you've been learned from other neurons and so forth that you would then have the opening of voltage-gated sodium channels. And these cells are a little bit different. The ones in that sinoatrial node have calcium spikes, and so there's opening of voltage-gated calcium channels in response to depolarization. And there's an influx of calcium ions. These are positive, and so that will depolarize the membrane. So then once we hit spike threshold, the membrane potential goes up. Now, eventually we will have potassium channels, which are also voltage-gated. They open in response to depolarization, but they're slow to open. And as they open, and then then there's an efflux of potassium, and this leads to the membrane potential repolarizing, going back down again. This repolarization causes the membrane to hyperpolarize, and then that causes an opening of the HCN channels, which then, through sodium influx, gradually drives the membrane potential back up again. And so that's how you get a rhythm going over and over again. Now, I should mention that the hyperpolarization activated channels, or the HCN channels, part of their name is CN, and that stands for cyclic nucleotide. So they're also activated by an increase in intracellular levels of cyclic nucleotides, such as cyclic AMP. So as we discussed earlier, as you go from rest to exercising, there should be an increase in heart rate. That will lead to an increase in cardiac output, because cardiac output is stroke volume multiplied by heart rate. So as you begin exercising, one thing that will happen is that you will start to activate the sympathetic nervous system. That's often referred to as the fight or flight system that gets activated when you're in an emergency situation. Well, it turns out not only in that sort of extreme situation, but also when you're simply exercising or you're more active, so you're doing a brisk walk, then your sympathetic nervous system would in fact be more activated. And there are nerve endings of the sympathetic nervous system onto the heart directly at the sinoatrial node. And the neurotransmitter that released is norepinephrine. Norepinephrine will cause an increase in intracellular cyclic AMP. Recall that the HCN channels are hyperpolarization cyclic nucleotide channels. And so these channels will open as the intracellular cyclic concentration of cyclic nucleotide increases. And this will cause a faster depolarization of the pacemaker potential. So here's the normal control value. Here, if you stimulate the sympathetic nerves, there'll be greater opening of the HCN channels, and therefore you reach spike threshold faster. And then you have a spike faster, it repolarizes, and then the next one occurs faster also. So the overall effect is that the heart rate will increase. I should mention also that epinephrine released from the adrenal glands will also cause an increase in intracellular cyclic AMP. So in sense, we have two types of control here. One is neuronal, via the release of norepinephrine directly at nerve terminals on the sinoatrial node. And then we have a hormonal effect of epinephrine being released from adrenal glands. So let's imagine you've gone on a run and now you're doing a warm down, slowing down, just going back to walking, say. You would expect your heart rate to go down under these conditions, and that's exactly what happens. So what happens is that as you start to relax, then another division of the autonomic nervous system starts to take over, which is the parasympathetic nervous system will start to increase its activity. And so some of the nerves of the parasympathetic nervous system will release acetylcholine. The actual nerve is called the vagus nerve, and it supplies nerve endings directly to the sinoatrial node, where these nerve endings will release acetylcholine. The effect of acetylcholine will be to open potassium channels. And so potassium channels will being open will lead to the efflux of potassium from these pacemaker cells, and that will tend to hyperpolarize these cells. And so that will make it take longer to reach the spike threshold. So if you notice, here's the normal control condition. Now, if we have hyperpolarization, then during this hyperpolarization phase, you may go down a little bit deeper. And this rise up of the pacemaker potential, which is due to sodium influx, is opposed by potassium efflux. And so it takes a bit longer to reach the action potential threshold and for an action potential to be generated. So this means that there's more time between individual action potentials. Recall that each action potential corresponds to one heartbeat. And so this means that the heart rate will decrease. Mechanisms that affect cardiac rate are said to be chronotropic effects. So, for example, you may have a positive chronotropic effect. This is due to something that increases the heart rate, and something else might have a negative chronotropic effect, meaning that it decreases the heart rate. Now let's look in a little more detail at the effects of the parasympathetic nervous system and heart rate. Now these effects are mediated via the vagus nerve. So you can see in this diagram, the vagus nerve starts off in the lower portion of the brainstem called the medulla oblongata. So individual nerves have their cell bodies in the brainstem. They send axons through the vagus nerve, and they'll make synapses at two places. One is at the sinoatrial node, and the second place is at the atrioventricular node. At the sinoatrial node, there'll be a release of acetylcholine, and that will lead to a slowing of the heart rate. At the AV node, there'll be a release of acetylcholine, and this will lead to a slowing of the conduction rate of the atrioventricular node. Recall that the main job of the atrioventricular node is to allow, together with the bundle of His, also called the atrioventricular branch, is to transmit the electrical signal or electrical action potential of the atria to the ventricles, because there's a fibrous skeleton in the heart that prevents it from going through any other pathway. At the same time, the atrioventricular node has to also act as a delay site. So it delays the transmission of this action potential from the atria to the ventricles, allowing the atria to contract first before the ventricles begin to contract. Now, if you slow down the heart rate, you should also slow down the conduction rate at the atrioventricular node in order to allow for more time for the atria to contract before the ventricles contract. And so that's what's happening through this innervation of both the SA node and then the atrioventricular node. You have a slowdown in heart rate as well as this conduction rate. The sympathetic nervous system increases heart rate, and we can see how in this picture. It has cardiac accelerator nerves. These are spinal nerves. So this is coming off the spinal cord. You can see the cell body of a sympathetic neuron. The activation of these neurons leads to the release of norepinephrine, at synapses on the sinoatrial node, and this increases the heart rate by affecting the pacemaker cells. At the same time, there are branches of these neurons, so there's bifurcations, and they send branches to the AV node where they increase the conduction rate. And this actually makes a lot of sense. If there's an increase in heart rate, then the atria should contract, and then very quickly after that, the ventricles need to contract. And so if you had a large slowdown at the AV node, that would lead to the ventricles contracting too late. And so it makes sense that if with an increased heart rate, you should also have an increased conduction rate at the AV node. Now you notice another thing. So far that's sort of perfectly symmetrical between the sympathetic and parasympathetic nervous systems. But it turns out the sympathetic nervous system also does something else. You note that there's fibers going to the atrioventricular bundle, also known as the bundle of His. And so I couldn't find a really good reference, but presumably there it may also be increasing conduction velocity. Again, I couldn't find a reference for that, but certainly we know that there's the presence of sympathetic nerve endings there. So that's presumably what they're doing. And then you'll also see some innervation of the Purkinje fibers, which help to conduct the action potential up the walls within the myocardium. And then there's also synapses directly with cells within the myocardium. This is in other words, the cardiomyocytes that are actually involved in contracting the ventricles, as well as the atria. That's not shown here with the atria. So the idea, though, is that these connections directly at synapses onto the cardiomyocytes is that they have a very specific function, which is to increase the contractility. In other words, the force of contraction of these cells, both in the atria as well as in the ventricles. And that's different. Notice that the parasympathetic system has an effect on the timing of the heart rate, but has no direct effect on contractility of the cardiomyocytes. This table from your book summarizes the things we've talked about. At the SA node, sympathetic nerves increase the rate of depolarization of the pacemaker cells, and this leads to an increased cardiac rate. At the AV node, there's an increased conduction rate mediated by the sympathetic nervous system. Atrial muscles exhibit greater contractility when they're receive norepinephrine directly at synapses from the sympathetic nervous system. And the ventricular muscle also shows increased strength of contraction or increased contractility due to direct innervation by sympathetic neurons. If we looked at the parasympathetic nervous system effects, we find that at the SA node, there's a decreased rate of generation of the action potentials by the pacemaker cells in the sinoatrial node. This leads to a decrease in cardiac rate. If we look at the AV node, there's a decreased conduction rate, and then there's no effect whatsoever of the parasympathetic nerves directly onto atrial muscle or ventricular muscle. We're going to talk about the cardiovascular control center more in detail, but at least I want to introduce the idea here. Within your brainstem, within the medulla oblongata, which is the lower portion of the brainstem shown here, you have this thing called the cardiovascular control system. This center receives input from higher brain centers. It also receives input from other places such as the hypothalamus. It also receives sensory input from baroreceptors. For example, you have baroreceptors, which are pressure-sensitive receptors in the carotid arteries, as well as in the aortic arch. And so those monitor your mean arterial blood pressure. So this cardiovascular control center is essentially controlling the sympathetic and parasympathetic output that we've just talked about, and therefore they can increase or affect the heart rate as well as heart contractility. As I mentioned earlier, cardiac output is regulated or is dependent on stroke volume as well as heart rate. So we've talked about how heart rate can change, and that could therefore have an effect on cardiac output. Well, stroke volume is also something that can change. It's regulated by three things. One is the end diastolic volume, another is contractility of the ventricles, and the third thing is vascular resistance. So let's go through those three in order. So starting with EDV, or end diastolic volume, that's the volume of the ventricles at the end of diastole. So EDV is sometimes referred to as preload because it's the amount of blood that's filling the ventricles, and the ventricles will then contract against this load. So it determines in some sense the amount of work the ventricles will have to do. It will also determine the amount of blood that can be ejected. So logically, as you might think about this, as if the ventricles are filled with more blood, then they may eject more blood. And that's exactly what happens. With an increase in the end diastolic volume, you'll find that the stroke volume also increases. And we'll talk about that in a little bit of detail in a second. Now, the other thing that can happen, of course, is if you have greater contractility or force of contraction of the ventricles, this can also lead to an increase in stroke volume. And we've already discussed a little bit about how that can happen. So, for example, direct synapses, sympathetic synapses that release norepinephrine will increase contractility. Also, epinephrine acting as a hormone will also affect those cardiomyocytes of the ventricles, and it also increase contractility. The third variable that affects stroke volume is the resistance of the blood itself. So this is sometimes referred to as vascular resistance. It's the resistance that must be overcome to push blood through the circulatory system and create flow. So imagine the left ventricle must push blood out, and it's pushing against blood into the aorta and other major arteries that have a certain amount of blood pressure. So that essentially does limit to some degree the amount of blood that will be ejected during each ejection phase during systole. So let's look at a little more detail about these ideas. The resistance offered by the systemic circulation is known as the systemic vascular resistance, or SVR. And this is sometimes referred to as by an older term or called total peripheral resistance, or TPR. Your book uses this term, total peripheral resistance, so I'll try to make an effort to use that term. Occasionally I may slip and use SVR, systemic vascular resistance. And so, as I mentioned earlier, there's a different resistance to the two circuits. So the resistance offered by the pulmonary circulation is known as the pulmonary vascular resistance, or PVR. Okay, previously we talked about the idea of preload, which is the idea that the greater the end diastolic volume, there's a greater stretching of the ventricles, and therefore that leads to greater contraction and therefore higher stroke volume. And we're going to talk about that in more detail later, but the idea of preload is fairly well defined. It has to do with the end diastolic volume, or EDV, as well as the stretching of the ventricles. Now let's talk more about this idea of what's going to be called afterload. So as I mentioned, as we've talked about before, a fluid always moves from an area of high pressure to low pressure. So during the ejection phase, let's think about the left ventricle. The left ventricle is contracting and blood is being ejected into the aorta. And the reason for that is because the aortic pressure is lower than that of the ventricular pressure. So the load, which is essentially this force that opposes the movement of the fluid, has to do then with the pressure within the aorta. And what determines that pressure? Well, one of the biggest determinants of that pressure is what's called the resistance within the systemic circulation. And as I mentioned earlier, that could be called SVR, systemic vascular resistance. It can also be called TPR, for total peripheral resistance. So one idea is that the higher the TPR is, then that will lead to a higher mean arterial pressure, or MAP. And so that then determines, as the left ventricle is working to push blood into the aorta, the higher the mean arterial pressure, the more difficult it is for it to do its work, to eject blood into the aorta. So afterload is sometimes thought of as or quantified by looking at these pressures. So In one study, they might look at mean arterial pressure. Sometimes they may use systolic pressure. I think it's more common just to use mean arterial pressure. But what I'm trying to say is the term afterload it's a concept, and the way it's actually measured may vary between one study and another, and so forth, and what people may use it slightly differently. But conceptually, it's basically the idea that when you eject blood, you're going from an area to high pressure to low pressure, and the higher the pressure in the aorta, then the more work that the heart has to do, and therefore that constitutes a kind of load that it has to work against. And so the basic outcome of all this is that as the total peripheral resistance increases, well, that will increase the mean arterial pressure, and therefore stroke volume will decrease. Typically, about 60% of the end diastolic volume is ejected per heartbeat. So this is known as the ejection fraction. And so, for example, if I gave you a problem like this, you should be able to solve it. So if we have an end diastolic volume of 120 milliliters and a stroke volume of 70 milliliters, what's the ejection fraction? Well, the answer is it's simply 70 milliliters divided by 120 milliliters and then multiplied by 100 to yield a fraction. And so the answer here in this case would be 58.3%. Which is pretty close to this sort of standard value of 60%. So the interesting thing is the ejection fraction remains constant. So let's take our person who's going from rest to suddenly exercising. Up to a certain point, as long as they're not doing, if they're going from rest to just sort of light exercise, you'll find that the ejection fraction remains more or less constant and will stay about 60%. Things change a little bit when we get into really strenuous exercise, but we're not going to talk about that for now. So what happens is that during exercise is that the end diastolic volume will increase. Why is that happening? Well, if you're running, say, there's more venous return of blood back to the right atrium. And then this means that in order for this ejection fraction to remain constant, as EDV goes up, then the stroke volume must also increase by a corresponding amount. And conceptually, what this means is that the strength of ventricular contraction must increase to maintain the same ejection fraction. And the next topic we'll dive into is called the Frank-Starling law of the heart, and we'll talk about exactly how this happens. Otto Frank and Ernest Starling were two different physiologists whose names have now been combined forever into the Frank-Starling law of the heart. And so what they both demonstrated was that as the ventricular end diastolic volume increases, there's an increase in stroke volume, okay? And furthermore, this occurs in a heart that's essentially been taken out of an animal. So it's kind of horrible, but if you take the animal out of the heart out of an animal, and the reason for doing this is now there's no possibility that there's any sort of feedback mechanisms involving the nervous system. Well, this phenomenon still occurs. As you increase the end diastolic volume, the stroke volume increases. And so the practical outcome of this is as you put more and more blood in, using, say, a machine into the ventricle, then it always is able to eject enough blood by increase out of it. So the stroke volume increases, and it never gets sort of overwhelmed by this blood that you're putting into it. And furthermore, what they figured out that the reason for this is that there seems to be an intrinsic property of the heart. In other words, it's a property that's not dependent on neural feedback or anything like that. It's an intrinsic property of the heart itself, the walls of the ventricles, such that as you increase the end diastolic volume, there's an increased contractility, and then that leads to this increased stroke volume. And this happens over quite a large range of stretch. In other words, you can put a little bit of blood into the heart, into the ventricle, or you could put a lot more into it. And as you keep putting in more and more blood, it always ejects more and more. It turns out that there are two mechanistic explanations for this intrinsic control of contraction strength. The first has to do with myocardial stretch. So as you put blood into the ventricles, they stretch. This stretches the actual muscle cells, the cardiomyocytes, and so the idea is that as they get stretched more, then they exhibit stronger contractility. They contract with greater strength, and that's shown in this graph here. We have tension here on the y-axis. We have time showing you stretch of individual cardiomyocytes. I mean the time course of the twitch due to single action potential in cardiomyocytes. So for example, here in A, we have a cardiomyocyte that's already pre-contracted. You can see here one sarcomere here, and there's even overlap of the actin filaments at the M line, across the M line, and notice that the thick filaments, which are composed of myosin, are right at the Z discs. So if you stimulate a cardiomyocyte that's already sort of been stimulated already, so it's already pre-contracted, you get very little tension out of that. And that actually makes sense because of all this overlap. There's less possibility of cross-bridge formation between the actin and myosin filaments because of the overlap of the actin filaments. And also notice that the myosin filaments are literally physically bumping into the Z disc, so you can't really get that much tension generation. And then you notice what they're doing is they're stretching this cardiomyocyte. And as you stretch the cardiomyocyte and then you stimulate it experimentally, you see greater and greater amounts of tension. And the reason for this, and it's actually very difficult to see in the way this diagram is drawn, but the idea is basically as you stretch the cardiomyocytes more, there's more region of overlap between the thick and thin filaments where cross-bridge formation can occur. And so there's, for example, in D, there should be the most overlap and therefore very strong tension. Now, if you take this further, and they're not showing this further, but if you stretch the single cardiomyocyte even more, such that there's no overlap between the thick and thin filaments within the sarcomere, then the tension would be very low because there's simply no cross-bridge formation. And they're just simply not showing that here in this diagram. But basically the idea is that as you stretch the muscle more and more, up to a certain point, there'll be more and more tension, in other words, force generated. And that's because of this increased cross-bridge formation between the two types of filaments. Now, there's a second reason. So that's the first one. The second one is because as you stretch these cardiomyocytes, there's also an increased sensitivity of the channels within the sarcoplasmic reticulum that release calcium into the cytosol. And so those channels become more sensitive, and they're going to open up. There'll be more opening of those channels, and therefore more efflux of calcium out of the sarcoplasmic reticulum into the cytosol, and that also leads to stronger contractions. So a reasonable question would be, why do we need this intrinsic control of contraction strength? Well, it turns out we have it for a very good reason. Let's imagine that you have, for some reason, an increase in total peripheral resistance, or TPR. Well, that's going to decrease the stroke volume because it'll increase the mean arterial pressure. And so on one given cardiac cycle, you may have a little bit less blood ejected. But immediately, because you'll go right into diastole, so the ventricles will now get filled. And since it started with a little more blood to begin with, EDV, or end diastolic volume, will be increased. And therefore, because of the Frank-Starling law of the heart, the ventricles are stretched more, they're going to contract with more force, and therefore there'll be a bigger stroke volume right away. So almost cycle by cycle, the heart is able to adjust for any fluctuations in the blood coming back to it. So for example, the other example would be, say, the right side of the heart for some reason was to pump a little more blood in one cycle to the left side. Well, almost immediately the left side would respond to that increased end diastolic volume by contracting with more force and therefore ejecting more blood and having a larger stroke volume. And so this keeps everything in a very nice balance. So far, we've discussed intrinsic control of contractility of the cardiomyocytes in the ventricles. And that's largely due to the Frank-Starling law of the heart. In addition to that, there are also extrinsic mechanisms that control contractility. Contractility is the strength of contraction at any given fiber length. So norepinephrine released at nerve terminals and epinephrine acting as a hormone can both increase contractility. Let's take a look at this graph. So we have on the x-axis ventricular end diastolic volume. Remember, as we increase the ventricular end diastolic volume, we increase the fiber length. We're stretching the fibers more. And then the y-axis, we see stroke volume. You can think of stroke volume, obviously it's the amount of blood that's ejected per heartbeat, but it also can substitute in for contractility of the heart, because for a given fiber length, if we have a larger stroke volume, that means that there was a greater contractility of the heart. So again, let's look at this graph. If we pick a point and we say, okay, here we have a given fiber length and we have a certain stroke volume, okay? Now, if we stimulate the sympathetic nervous system and we have norepinephrine released at nerve terminals, and remember that some of these terminals will go directly to cardiomyocytes in the ventricles as well as cardiomyocytes in the atria, and they'll stimulate these to contract with more strength. And epinephrine will actually, acting as a hormone, will have a similar effect. So if we add sympathetic stimulation, now for a given fiber length, we'll have a larger stroke volume. And recall that I just said that stroke volume can be thought of as a way of indirectly looking at heart contractility. So this means that there's an increase in contractility. So if we see this sort of phenomenon, that's considered to be a positive inotropic effect. The term inotropic refers to something that increases or decreases the force of muscular contractions. A positive inotropic agent increases the strength of muscular contractions. A negative inotropic agent decreases the strength of muscular contractions. Recall that the parasympathetic nervous system has nerve fibers that go to the sinoatrial node. They release acetylcholine and have a inhibitory effect on the pacemaker cells there. They reduce the heart rate by acting on those cells. At the same time, these parasympathetic fibers also go to the AV node, but there are no parasympathetic nerve fibers that go to the myocardium, in other words, to the cardiomyocytes that are directly involved in generating the contraction. So you would think that there should be no effect whatsoever of the parasympathetic nervous system on the stroke volume and contractility. And in fact, there isn't any direct effect. However, there is an indirect effect. So the release of ACH at parasympathetic terminals on the SA nodes leads to a decrease in heart rate. This decrease then leads to more time for ventricular filling. Therefore, there's an increase in the end diastolic volume. The increase in this end diastolic volume then leads to an increase in the degree of stretch of the cardiomyocytes of the ventricles. Then, according to the Frank-Starling law of the heart, there'll be an increase in intrinsic contractility of the ventricles, and therefore there will be an increase in stroke volume. So as heart rate goes down due to a lot of activity of the parasympathetic nervous activity, you will in fact see an increase in stroke volume. Cardiac output itself will actually drop, and that's because recall that cardiac output is the product of stroke volume and heart rate. And so the decrease in heart rate means that there'll be overall a decrease in cardiac output. And so that's why certain drugs such as beta blockers, which block beta adrenergic receptors at the SA throughout the body, but specifically they're going to act at the SA node, a sinoatrial node. They'll block the effect of stimulatory effect of norepinephrine on the sinoatrial node, and therefore that will decrease the heart rate, and therefore this may lead to an increase in stroke volume, but overall there'll be a decrease in cardiac output. In this graph, the relative tension is plotted such that it's 100% when the length of the muscle, whether it be skeletal muscle or cardiac muscle, so it's 100% when the length of the muscle is at its optimum. So we'll call that 100% also. So, and then we're going to shorter and shorter lengths. So for example, for skeletal muscle, once you get to 60% of this optimum length, which is the normal sort of relaxed resting length of the muscle, then you have zero tension development. For cardiac muscle, you also eventually drop to zero by the time you get to around 60%. Now, it turns out though that the slopes are a bit different. So with skeletal muscle, you get a more gradual decline in relative tension as if the muscle is sort of pre-contracted essentially before you stimulate it and then measure the relative tension. Whereas with the cardiac muscle, this slope is much steeper, meaning that for a small change in the length of the muscle, you go to much lower tensions quite quickly. And so this is actually quite important. So this means that the force generated by cardiac muscle shows a steeper dependence on muscle fiber length compared to skeletal muscle. And this goes back to the Frank-Starling law of the heart. This dependence is very important for cardiac muscle. As we say we have a certain length of muscle because remember, we can correlate end diastolic volume with the length of the muscle. So let's say we have a certain amount of stretch because we have a certain end diastolic volume. Now, for whatever reason, there's an increase in end diastolic volume because there's more heart blood returning to the ventricle for whatever reason. Now the cardiomyocytes of the ventricles are stretched, but suddenly there's an increase. There's a relatively rapid increase in the force generated by the cardiomyocytes in the ventricles, and so then that allows them to inject a lot of blood during the ejection phase of systole. And so this is actually very important, the fact that this is so steep. And there's a curve here, but simply the slope of this curve is less steep for regular skeletal muscle now compared to cardiac muscle. And then here we can see with epinephrine, if we add epinephrine and do this experiment again, then this whole curve for cardiac muscle is shifted to the left. And this means for any given length, there's going to be an increase in the amount of force generated. And again, that's consistent with the ideas of what we've been discussing with epinephrine. So it increases contractility, and epinephrine is a positive inotropic agent. This diagram puts together a lot of the things we talked about. Cardiac output is the product of cardiac rate and stroke volume. So we talked about the fact that parasympathetic nerves can release acetylcholine at the SA node, and they can inhibit the SA node and decrease the heart rate. Sympathetic nerves release norepinephrine at the SA node and thereby have an excitatory effect and increase heart rate. Now, sympathetic nerve fibers can also go to the cardiomyocytes that are involved in contraction in both the atria and the ventricles, and the release of norepinephrine on those cells leads to an increase in contraction strength, which can lead to an increase in stroke volume. Now, we also talked about the fact that end diastolic volume also has a stimulatory effect on stroke volume. The higher the end diastolic volume, the higher the stroke volume. And the reason for that is shown here. With a higher end diastolic volume, there's more stretch of the cardiomyocytes. And via the Frank-Starling law of the heart, we know that this will lead then to a greater intrinsic contraction strength, and that leads to an increased stroke volume. Finally, there's also the effect of the afterload on stroke volume. So the afterload can be thought of in different ways. One way of looking at it is to look at the total peripheral resistance. So this is the resistance to flow of blood. So the higher the total peripheral resistance, the lower the stroke volume. Now, very closely related to total peripheral resistance is the mean arterial pressure. The higher the total peripheral resistance, generally you're going to have a higher, with all other conditions being equal, you'll then have a higher mean arterial pressure. So you can think of that also as being another way of looking at afterload, which is that the left ventricle has to eject blood into the aorta. If the mean arterial pressure is high to begin with, then it's more work essentially for the heart to inject blood, and therefore the stroke volume will be lower. We've established that end diastolic volume is very important for stroke volume and therefore important for cardiac output. Well, it turns out there's another factor that we need to take into account. That's the venous return. The end diastolic volume is controlled by factors that affect this venous return. And there's basically two ways we can look at it. One is total blood volume. That's going to have a big impact on venous return. The larger the total blood volume, the greater the venous return. And the other thing is venous pressure, which is a driving force for blood return. The first thing we need to understand are the differences between arteries and veins. Arteries and veins are similar in some ways, but there are also some really key differences. Veins hold more blood than arteries. If we look at this diagram here, we can see that a certain amount of blood is found in veins, there's a certain amount in capillaries, and then about 60 to 70% of your blood at any given moment would be found within veins. And we're talking about small veins and venules as well as large veins. So overall, about 2/3 of your blood is found in your veins. And for this reason, they're sometimes referred to as a volume reservoir. The reason they're considered a reservoir is if you do lose blood, then you essentially have a little bit of extra blood that we can draw upon in those situations. Veins also have, and related to this is the fact that veins have a very high compliance. The term compliance means that if you apply a certain amount of force, the veins will stretch, and they're more compliant than arteries are. Arteries obviously are compliant. So for example, we talked about the aorta and the major arteries. They are compliant, they stretch, and then they're very elastic, so then they have an elastic recoil. Well, veins are compliant in the sense they'll stretch, but then the elastic recoil is not as great. So they comply, meaning that you apply force, and then they stretch and they increase in diameter. So this compliance of the veins allows them to act as the volume reservoir. They can increase in volume and therefore take up blood if need be. Another major difference between arteries and veins is that arteries generally have a fairly high pressure. So if we look at the aorta or the major arteries, such as the brachial artery in your arm, they have a mean arterial pressure of around 100 millimeters of mercury. By the time you get to arterioles, the pressure is lower, but it's still fairly large. If we look in the venous system, the pressures are much lower. So by the time blood arrives in the venules, the pressure is only 10 millimeters of mercury. And by the time the blood arrives at the right atrium, it's effectively about 0 millimeters of mercury. So it's very low. So this means that pressure is a driving force, but it's not as much of a driving force for the movement of fluid within the venous system. And that's why we have certain things which we'll talk about in a second, such as the respiratory pump, the skeletal muscle pump. There are a whole bunch of different mechanisms that you have in your body to help move blood back in the venous system towards the heart. Okay, so venous pressures are very low. And we can ask the question is, why is venous pressure so low? Well, one thing is it's just due to the fact that veins come after the arteries. So you have resistance to flow, which is primarily due to friction. And a lot of that friction, although some of it is due to the friction within the fluid itself, a lot of it's due to the friction between the fluid and the walls of the vessels that the fluid is moving through. And so pressure can be thought of as potential energy. It's converted to energy of movement or kinetic energy, so this leads to blood moving through the cardiovascular system. But it rubs against the walls essentially. So there's friction, and then you generate heat that way. And so clearly, as you go around further through a circuit, as you get further and further away from the pressure source, which is the heart, then there'll be a decrease in pressure as this heat is generated through friction. So that's certainly one aspect of it. But then the other thing is that the venous vessels are so compliant that when the blood does enter into them, they tend to stretch and they increase in diameter. And that leads to an increase in surface area that the blood is pushing against. Now we have to remember what the definition of pressure is. Pressure is defined as force acting perpendicular to a surface. So again, we can think of like pounds per square inch. So pounds is a unit of force, per square inch has to do with the surface area. So if we increase the surface area, then there's a decrease in pressure. So the fact that the veins are so compliant that they have a large surface area also leads to this low pressure in the venous system. So let's imagine a situation in which you actually have, say, a lower blood volume. So a decrease in blood volume means there's less blood in the venous system, and therefore less pressure. Well, in that case, what would happen after, say, you donate blood is the sympathetic nervous system will become a little more active. It will stimulate smooth muscle to contract, and this will lower the compliance. It'll constrict the blood vessels in the venous system. This reduces the surface area and thereby increases the pressure within the venous system, and that will aid in the return of venous blood to the heart, to the right atrium. Additionally, let's take another situation. You have a person who's now, say, running, and so they need a lot of cardiac output. So to keep mean arterial pressure high, so they need blood coming back to the heart. Well, conveniently, as you run, the skeletal muscle pumps are very active. We talked about this previously. These are essentially these pumps are formed by these chambers within the veins, major veins, which are deep within your legs and in your arms. They have one-way valves, and when they're squeezed, they essentially generate pressure by push blood towards the heart. So as you become more active, there's an increase in pressure due to the fact that you're pushing blood towards the heart. So that helps with the fact that the venous system vessels have such a low pressure to begin with. There's also the respiratory pump. So as you imagine the person running, they're breathing hard and fast, and there are pressure differences between the abdominal and thoracic cavities. Recall, as the diaphragm is pushed down, there's a decrease in the volume of the abdominal cavity, and therefore there's an increase in the abdominal pressure. At the same time, as the diaphragm contracts and moves downward, there's an increase in the volume of the thoracic cavity, and therefore a decrease in pressure there. And the inferior vena cava has valves, just like the other major veins, and therefore blood moves via this pressure difference upwards towards the heart. So again, the more active you are, there's an increase in pressure as you push this blood back towards the heart. So this does help. And then finally, blood volume. In certain situations, let's say you would you lose blood due to an accident. Well, your kidney will start to work to you'll drink. First of all, you feel thirsty and you'll drink water, but also your kidney will help to retain water in your blood, and this will help to maintain and even increase the blood volume. And so so you have more fluid inside the arteries and veins, and this increases the pressure also. So all of these things would help, are factors that would help in venous return. Finally, this is just a diagram putting it all together. So end diastolic volume is very important for stroke volume, and that helps feed into keeping the cardiac output sufficient at any given time. And so venous return is very important for maintaining end diastolic volume. So one of the big factors that influences venous return is blood volume. That's affected by urine volume. So for example, if your kidney produces a large volume of urine, this would decrease your blood volume. So for example, if you had high blood pressure, perhaps your kidney would create a higher blood volume, and this urine volume, this would decrease blood volume. Also, your extracellular fluid can be in different compartments. We have the blood plasma, and then we have interstitial fluid. So another possibility is perhaps if fluid is drawn into the interstitial space, that would decrease blood volume. So that's another possibility that could happen. Now, negative interthoracic pressure, this refers to the respiratory pump. So as you breathe, you increase pressure. As your diaphragm descends, you have increased pressure in the abdominal cavity and lesser pressure in the thoracic cavity, and this helps to push blood back towards the heart. Venous pressure is affected by a lot of things. One is skeletal muscle pump. So we talked about the fact that this, with these one-way chambers in your arms and your legs, this helps to push blood back. So that increases venous pressure, which helps with venous return. And venoconstriction is also very important. So you have sympathetic innervation, meaning there's sympathetic nerves that innervate the major veins, as well as small veins, as well as the venules. And so you can have vasoconstriction, and this will also increase venous pressure, and this will also help with venous return.